Hi guys, I am Jen Manzo with HVAChicks Coalition. I am here with Mr. Jim Bergman. You all know who that is on this measureQuick YouTube channel this morning. I'm doing some research for a project that I'm doing for HVAC Know-It-All for a blog that I'm writing, and it's all about non-invasive system checks. So this is something that I preach to everybody. This is something that Jim also is fond of. So I wanted to get together with Jim, kind of asked him his expertise about how he feels about non-invasive system check. So, Jim, if you're ready, I'll jump right into the questions.
Sure.
All right. So, first of all, what is non-invasive system check? And for those who don't know, why is it important?
So non-invasive testing just simply means testing without attaching a probe or a pressure probe or gauges to the equipment, right? The whole idea is the refrigeration systems is sealed system. So it's just like your home refrigerator, right? The last thing somebody would do if they're an HVAC tech is go get a set of piercing valves, pierce into the system and check the charge with the gauges, because they go, well, why wouldn't you do that? Well, it's a sealed system. It's sealed from the factory. It's like, well, everything we work on is a sealed system. We just got to start treating it that way.
Yes.
And so the whole idea behind non-invasive testing is that once we have a little bit of information about the system, we should be able to test everything with temperatures without actually hooking up the gauges. And that's going to reduce things like cross-contamination of refrigerant, introducing moisture into the system, refrigerant loss in general, even things like leaving the caps off after you service it, right? It just keeps the sealed system sealed.
It's almost as if to me that we made gauges and then we just used them no matter what. We just used them no matter what. When I was taught HVAC, I know that I was literally taught, these are your analog gauges and this is what you hook up every time you walk up to a system. I only learned later that that was not correct. What about manifold versus probes? Are we contaminating the system less, do you feel, when we use probes than we are when we're using a manifold?
Well, we're probably contaminating it less because your refrigerant hoses, they get a coating of POE oil, and that POE oil is really hygroscopic. And unless you keep your hoses meticulously capped or keep them under pressure, you're going to end up with a trace amount of oil and water in the system that are going to get transferred when you put new gas into your system. Usually that's managed by your filter dryer, but like in case of mini splits, they don't have a filter dryer. So the only way for the moisture to get managed is it's just got to be so scarce that it doesn't really contaminate the refrigerant excessively.
Right.
And so when you say that's what you were taught, it goes back to, like, if you think about a barbershop, bloodletting, and the scalpel was their only tool. So what did they do? They used the scalpel, they let blood out of the person, and hopefully they're going to survive the situation. But that's the tool they had. And that's the same thing we do today. It's like gauges are our only tool. So what do? You hook up the gauges.
Right.
The big epiphany for me with gauges was when I realized I didn't really know what the pressures were going to be before I hooked the gauges up to the system.
Yes.
And then I'm like, well, why am I hooking them up to start with? Right.
Exactly.
Like what value is this? If I don't know what the pressure should be exactly, what value is hooking them up?
Right. But
yeah, it was way too high.
To know why.
If they're like way too high or way too low, but right. If you're going to make a measurement, you really should know what the measurement is before you hook the gauges up to the machine. Right.
Absolutely. So. Yes. And also, what would you say is a reason that we have to hook up gauges where non-invasive system testing isn't enough at that moment?
Well, I mean, it just when the temperature relationships no longer hold true. I mean, primarily we're looking at temperature split. If you measure airflow, like let's say use a true flow grid or an anemometer, some way of measuring airflows, so a static pressure in a table, whatever you got, you measure airflow and your airflow is in the right range. Then you measure your temperature split across the coil and the temperature split looks good. And, we can also measure suction and liquid line temperatures because we can back calculate exactly what those should be. But if for some reason the temperature split or the line temperatures are not in the range that we expect them to see then, and obviously the coils are clean, the condenser's clean, the filter's clean, the basic maintenance is done, then we probably need to hook up gauges to the machine. And that's going to be on somewhere between 30 and 70% of systems, sadly, are going to require us to hook gauges up because that's a typical percentage of them that have a charge issue.
Yeah. And you guys also, I just want to add here that sometimes that charge issue is so many technicians hooking up gauges.
Yeah.
That one system that probably would have been all right if 50 of us didn't come within the last 2 years and hook up gauges. So
yeah, quarterly maintenance on rooftops and stuff like that.
Yes.
Everybody hooking up gauges is a huge issue. And you know as well as I do, like when we're switching refrigerants now, we're going to go to 454B and R32, and the chance of cross-contamination is going to be huge because now we have refrigerants that are very similar in pressure temperature relationship. So, this is where you might want to have dedicated, if you're going to use hoses that have ball valves or have check valves on them, you're going to want to make sure that you use dedicated sets of gauges for those new refrigerants, because even though some of these refrigerants like have R32 in them, or they're very similar to 454B, they're not going to, if you mix them together, you're going to end up with Dalton's law of partial pressures where you're going to get some kind of new refrigerant. It's not going to be the right mixture anymore, and it's not going to follow the temperature pressure relationships, and that's going to be a huge problem. So, we really need to get in a mindset now of hooking up the gauges 2 times in the system's life, when it's initially commissioned and when we dispose of it, right? There's really no other reason you need to hook up gauges in between.
Yeah. So one of my questions was going to be, during the life of a system, how often should we be hooking up gauges? And you guys, that's what Jim's saying, is that this is how important it is that we learn how to test a system without hooking up gauges. So Jim, you feel that it will be a lot more important with these new refrigerants to not cross-contaminate. And in that situation, we need to be able to not hook up gauges at all, or probes. So how are some ways that we can do that? What are some measurements we can take and read that will help us during a non-invasive system check? What would you take for temperatures?
I mean, the first thing you got to understand is what's called design temperature differences. And that's how much colder is your evaporator coil than your return air, and how much hotter is your condenser than your outdoor air, right? The temperature, when we do hook up gauges, we measure pressure. That corresponds to saturation temperature. That saturation temperature then is the driver of the heat energy. It's either, heat always moves from hot to cold. So the difference in temperature is what's going to impact the rate of heat transfer. So if we have a colder coil, heat's going to transfer into it faster. And by design, air conditioning systems are typically at 400 CFM per ton, have an evaporator coil that's 35 degrees colder than the return air. I mean, it doesn't matter what manufacturer you go to, because they're all bound by physics. They're going to move the same quantity of heat with the same velocity or same volume of air going across the coil. It has to be about at the same temperature difference to get the same results. I mean, we're engineering systems, we're sort of bound by physics.
Right.
Now, you may have a manufacturer that goes with like instead of a typical 40 degree coil, they go with a 45 degree coil.
Right.
But then you might have a larger coil, a surface area, and a decrease in the temperature difference. But if we just start with saying, okay, typical 35 degree design temperature difference. And let's say that we have a fixed orifice system and we calculated the target superheat was 13, right? So if you took 75 degree return air minus the 35 degree design temperature difference, that's a 40 degree coil. So that's our 40 degrees is our saturation temperature. And then if we add 13 degrees to it, so 13 degrees of superheat, because the suction line temperature is above the saturation temp. Yep. So 40 plus 13 would be 53 degrees. If our suction line was plus or minus 5 degrees of 53 degrees, then we're in the right range, right? So it's just really simple. Just do a little bit of math in your head and do it that way. Now, on the condenser side, typically a modern condenser is about 20 degrees hotter than the outdoor air. Right. So if it was 80 degrees outdoors, 80 plus 20, we'd have 100 degree condensing temp. And then if we had 10 degrees required subcooling, just take your 100 minus 10 is 90 degree liquid line temp. And if you're within 3 degrees or 5 degrees of your liquid line temp, you're probably fine. Typically, when we charge, we're going to be plus or minus 3. But if we're doing non-invasive testing, we could be plus or minus 5. And like there's diminishing returns. Like if I'm within 5 degrees of my liquid line, adding another tiny bit of refrigerant to get the subcooling down to, let's say, if we're at, maybe 7 and I want to get it to 10, it's probably not going to change the performance of my system that much that it's, and there could be uncertainty in my measurements. So you got to look at, what's also, this is where I look at temp split. Like if my temp split's in the right range and my subcooling's within reason, I'm just going to leave it. I'm not going to go in and monkey with that charge every single time, because there's going to be no positive benefit for the consumer, and the chance of creating a problem's higher than it is fixing one.
Absolutely.
Right? Yeah. I mean, but when we do charge, like initially, we want to do it as accurately as possible. I mean, if we have digital gauges and we can get within 1 degree of the subcooling target, that's what I'm going to do. I'm going to get it as close as I can when I have the gauges hooked up.
Yeah. And I just want to reiterate that that's the important time, you guys. That's one time where it's absolutely 100% okay to hook up your gauges. So you're going to use that time that you have, because you know that coming back on callbacks, coming back on service calls, that is not the time to be hooking up your gauges and dialing in charge. That's your time to be there troubleshooting. So when you have that opportunity after install on startup to dial in that charge as close as possible, don't be rushing to get out of there and leave your subcool out of whack, or make your VSATs where it needs to be. Do these things on startup.
And we have the whole non-invasive charging procedure in measureQuick that.
Yes, that's what I wanted to get to next.
Yeah. And it's really like, you don't have to learn any of the math. All you got to do is profile the system. So you tell us, what kind of metering device you have, and whether it's fixed or TXV or EEV, whatever you have on the system. You tell us what SEER your condenser is approximately, what your target airflow is, if you have an oversized evaporator coil. And then the software just does the calculations for you and figures out if you're in the right range or not, right? And obviously, you do need to do some things ahead of time. Again, you want to have a clean condenser and a dry condenser. You want to have a clean filter. The system's got to stabilize. You need to give it time for the algorithm and measureQuick to determine it's stable.
Yep.
But once you're through that point, you're pretty well good to go. Now, the interesting thing is, when we talk about non-invasive testing, is if we commission with measureQuick, we can do non-invasive to a much more accurate level, because we were talking in general, the evaporator coil is 35 degrees colder than return air. Well, what if you're at 375 CFM per ton instead of 400, or you're at 425? Because you got 4 blower speeds to pick from, and you pick the one that was closest, that, that maybe give you a little bit better dehumidification or a little bit more sensible cooling. Your coil is going to be a couple degrees hotter or colder than 35 degrees,
right?
Colder than return air. So this is where measureQuick, when you benchmark it, it records the exact design temperature difference for the evaporator coil, the exact design temperature difference for the condenser, the exact superheat or subcooling that you set it up with, the exact static pressure that you had when you installed it. And so we have all this information that we can now much more accurately assess the system and do diagnostics on the system without having to hook the gauges up.
You have that person, that lead tech is what I always tell my apprentices, that measureQuick is your lead tech if you don't have one, because measureQuick will tell you not only that, yes, something is wrong based on the parameters that you've given us, but also this is why it could be wrong, and this is how you could be able to fix it, which is super helpful.
Right. It's a piece of software, so garbage in, garbage out. You got to make sure that you're putting good information in the software so we can get good information out of the software. So that's where like profiling is so important, to be able to profile the system and to do some basic things. But the key thing is that you need to understand, a lot of people don't understand, is that the reason we measure pressures is to get temperatures.
Yep.
Temperatures are the driving force for heat transfer. And then the reason we're measuring superheat or subcooling is to assure that we have a full common liquid going to the metering device, and assure that only vapor is coming back to the compressor.
Exactly.
And so, obviously we want to have a fully active evaporator, right? So that's another important thing to do. Yep. And then in your market, you have a lot of mini splits, right? So, well, I'll give you a little quiz. I'll give you the Brian Orr treatment where I run into the ringer. What is the condition of the refrigerant when it leaves the small line out of a mini split? I'm not even going to tell you what it is.
It's just a discharge line, right? So
not the discharge out of the compressor, but the small line leaving on the line set between the
the one that's not the liquid line.
Yeah, the one that's not the liquid line.
I actually don't know. So it's what, high pressure, high temperature?
A heat pump is hot, but it's saturated liquid, right? It's saturated liquid. If you're in a cooling mode, it's saturated liquid.
If it's just for AC,
out. Yep. And what is it coming back then?
So it's coming back saturated vapor.
All right, saturated vapor, or in this case, most of the case on a mini split is saturated, but because it could be between 0 and 5 degrees of superheat. So it's either slightly superheated or it's saturated, right? Because on a mini split, it's about 5 degrees of superheat. Now, if it's saturated liquid coming out, well, if it's 40 degrees saturated coming out, what temperature would it be coming back?
More than 40 degrees.
Well, if it's saturated, it'd be the same. It's saturated out, saturated back.
It would be the same. Yes.
It'd be exactly the same. You'd have a fully active evaporator coil.
Right. Because it's not saturating.
You have liquid going out and liquid coming back. So if it's 5 degrees warmer than the saturated temperature, then it's superheated.
Right. Yep.
So on a mini split, if I have it in cooling mode and I measure the temperature of the saturated liquid line going to the head unit, and I measure the temperature of the suction line coming back from the head unit, there should be between 0 and 5 degrees difference between those two. And if there's not, then you've got an issue with a refrigerant charge.
Jim, you may have just saved my life with mini splits.
Yeah. Yeah. Because
writing that down.
Yeah, because that's what you got to look for. I mean,
They're
it's
so hard
just
to troubleshoot. They really are.
well, and I always want you to just take all the gas out and reweigh the gas back in again. And you can test. You can like a multi-head mini splits. You can get 6 sets of probes out and just turn on all the heads, turn on all the fan speeds on high, and make sure that you have between 0 and 5 degrees of superheat on every head. Wow. The thing is, they use an accumulator on a mini split, so that if it does come back saturated, it goes into the accumulator before it goes into the compressor. So the compressor is always protected.
Right.
But until the mini split's fully, modulated up and running at full inverters running at full speed, it doesn't have enough suction to pull all that refrigerant out of the accumulator, put it into the heads.
Right.
So it ends up with a pool of liquid refrigerant and oil in the bottom of the accumulator.
And also, some people use that accumulator as a storage tank, shall we call it?
Well, that'd be more of a receiver, right? If you had
exactly. It's not a receiver.
It's not a receiver.
Awesome. I have already learned so much in this little bit, and I was the one writing the article. So this is great, Jim. Thanks.
Yeah.
So another big question was, we are going to have a lot of junior techs that are going to be reading this, these technical articles. The big thing is what tools. So we all know that gauges are out because we're going non-invasive right now. So if we're there for a non-invasive system check, if we're there for maintenance, what tools would they need to have? What kinds of probes would they need to have? What types of clamps would they need to have? These kinds of things.
So we need to measure outdoor air temperature because we need to know what the outdoor air is so we can figure out if we're above or below the outdoor, so we know basically have reference outdoor air. Right. We need to measure liquid line and suction line temp so that we have those two temps. Then we need to measure return air, wet bulb and dry bulb, because we need to calculate target superheat if we have a fixed orifice, and we need a dry bulb temperature for the evaporator coil DTD. And then we need a supply air temperature to measure temperature split. So pretty much everything but the pressure probes.
Yeah. So the same kit you guys already have with your probes, just pull out everything but your probes.
So now let me ask you another question. Let's say we got a mini split and it's running normally and we have an amp meter clamped to it and you start adding refrigerant and overcharging it. What's your amp draw going to do?
You're going to have over amperage.
So another thing we can do is, and it's just sort of a sanity check, but
this is great. I was going to ask you about this. This is great.
If you were to, so I told you between 0 and 5 degrees of superheat, but once we have 0, we don't know whether we're overcharged or not, right? And so the next thing we want to check is our amp draw on our unit.
Love that.
So if you take and I usually do watt draw because a lot of these are rated, you'll see the watt draw on the unit.
Yeah.
So if you think about on a 95 degree day, that's what it's designed for. That's AHRI design conditions. So if the system was rated, let's say at 1,000 watts, on a 95 degree day, it should be drawn about 1,000 watts, right? And so if we were to say, well, if it was a 70 degree day, it'll draw about 70% of that. And it's just like a good rule of thumb. So if it's 60 degree day, 60% of that, 80 degree day, 80% of that. So 80% of 1,000 watts is 800 watts. So if we were to hook up and we were to measure 800 watts, let's say plus or minus 15%, and we were to measure 0 to 5 degrees of superheat, then we know that we're not overcharged. If we were measuring like 900 watts on an 80 degree day, then we'd probably know that we got a good chance we're overcharged. We want to weigh the gas out and weigh it back in. So it's very easy to tell, also because high amperage will be indicative of an overcharge on the system. And it just sort of happens to follow that rule of thumb. And it's a pretty linear relationship that probably because 95 is close to 100 degrees and it just happens to fall out. If you'd said, well, 95 is very close to 100, you go, well, 70% of 100, or whatever. It's just, I think it just follows that. It just happens to be that type of a weird linear relationship, but it works. It works pretty well. And that's what I usually do when I'm doing non-invasive testing is I'll on a mini split, I'll check between the two lines and I'll check the watt draw. And that's my sanity check. And obviously you can check temp split and things like that too. But
you guys, what Jim is saying is you still need to have all of those other tools that is in your tool belt. You still need to have all of your, thermistors, your temperature clamps, those kinds of things. And then once you've gone and found what your superheat is, like Jim said, you'll have between 0 and 5 degrees. If you're closer to 0, you're still not sure what to do. Go and take that amp draw. Cause like Jim is saying, we always think about needing to know what's going on with the refrigerant. Yes, we need to know what's going on with the refrigerant, but there are other ways to find out what's going on with the refrigerant than just gauging up. So.
Yeah. And sort of important today that you own a watt meter too. And, UEI makes one, Redfish makes one, Testo makes a nice one. I've just tested their 770-3,
Nice.
tested the UEI, tested the Redfish. They all work really good.
I have
But the reason we want a watt meter, a real watt meter, is because these units don't have power factors of 1, a lot of them. So
exactly.
you have, when you're talking about AC or circuits or inductive circuits or capacitive circuits, it's volts times amps times power factor equals watts. And if you don't have a meter that measures power factor, you're going to get a higher apparent power than you actually have.
Right.
Yeah.
Yep.
And that'll help you with diagnosing these problems really, really well.
Absolutely. And you guys, True Tech Tools has all of this. We have a discount code HVAChicks. Use it to get your watt meter for sure. That will help you so much with non-invasive system testing. All right, Jim, I think we have time for one more. So I guess the biggest one that I wanted to ask you, know how important it is now. We know that measureQuick can help us to do that. Other than going through, so we want to go through measureQuick with the bench. Can we talk about that a little bit more? I'm going to add my own benchmark to this article so people can kind of see what that looks like. But why is it important to do the benchmark when you're doing non-invasive system checking?
Think of it like your own personal medical record. When you go into the doctor, they measure your temperature, they measure your blood pressure, they measure your pulse, they measure your weight, and they're gathering specific information about you, right? They can look at a body mass index and go, you should weigh this much, or they know that a typical person is 98.6. So they want to understand you intimately and how you're trending. Are things changing? Every time you go to a doctor, they get a set of your vitals. In measureQuick, we sort of do the same thing when we do a benchmark. And the idea is that, every system is unique from the standpoint of it's got its own duct system. Which means that the airflow is going to be unique, and it's got its own line set length, which is going to change the operation of the system, and it's got its own installation characteristics, whatever other things that those may be. So what we're doing in measureQuick is we're optimizing the system operation. We're getting everything as dialed in as close as we can to the manufacturer specification. And then the software, when we hit benchmark, it just gathers a set of vitals about that piece of equipment. So it's the exact design temperature difference, the exact subcooling when you charged it. So if the manufacturer called for 10, they said plus or minus 3, and you were at 7,
right?
Well, you'd want to benchmark it, and you initially started at 7, because that's going to make our non-invasive testing a lot more accurate, because instead of subtracting 10 from 100, we're subtracting 7 from 100.
Yes.
So now I'm not wondering where the 3 degrees go, or do I have a refrigerant leak, or what changed? I'm not using a generic set of standards. I'm using the exact equipment operation today that I commissioned it. Yeah. So benchmarking just gives us a better starting place for that individual unit. And it's a unique signature for every single system.
Right.
And then additionally, like one of the things you're doing when you save a system to measureQuick is we're saving the refrigerant type, the metering device type, the make, the model, the serial number, the geolocation of the equipment, the information about when it was serviced, all kinds of things. So there's a record, like a medical record, we're keeping of that equipment as we go, and it's just going to make things easier in the future for technicians to actually service that system and service it really quickly, because now I just walk up, throw a couple of clamps on it, throw a few probes on it, and in the time it stabilizes, I have a really good idea if I need to go any further, just need to do a basic maintenance and cleaning. Right. So, yep.
I love
pretty
that.
Simple.
You guys, the benchmark thing is so important to me. I've been doing non-invasive system testing for a long time, since I learned about it a few years ago. And it was harder before, because like Jim is saying, if you don't have the benchmark that's unique to that unit, there's a lot more guesswork involved. You've got to say, okay, we don't know it is 7 until we have that benchmark. And when you guys use that, like Jim said, you keep going back to this unit every year to do their maintenance, and you know what it was last year, and you know why. And then it's just like leaving a service tag, but one that's so much more in depth than, I did maintenance on this unit. So.
Yeah. And it's shareable with everybody in your company. So it's not just information that you're privy to, it's information that everybody at the company has access to. And so now you're comparing your current readings to that of whoever commissioned the system. It happens quite a bit too, where techs are chasing each other and tweaking charge or tweaking airflow because they don't know any better, or they figure, well, I'm going to add a small amount of refrigerant or remove a small amount and see what happens. Yeah. Just non-invasive testing just makes that kind of behavior go away and eliminates a lot of issues.
It does. I love non-invasive system testing. You guys, the HVAChicks students that are going to read this article will see their non-invasive system checking on HVAC Simulator. You guys can check out that. In the field, you want to be using measureQuick. I don't know of another company that has this in-depth of a non-invasive system check with the benchmark, with the ability to run it through Diagnostics, through measureQuick. For training, you guys, HVAC Simulator has all of this. You can literally hook up your temperature probes on that. You can read your line temperatures. You can read, your evaporator. You can do all of that in a simulated situation where you can learn how to do it without going to the field and messing up your first few times, but you're still going to. So that's okay. All right, Jim. Well, thank you so much for joining me with this. I'm going to take this information and try to write a really good article about it.
Yeah. Do a search also on Lifecycle Refrigeration Management by Mowris, Mowris. There's a recent 2020 ACEEE summer study on energy efficiency in buildings, but he has a little bit different of a method of doing non-invasive testing.
Oh, wow.
But it does have some really good information on how much refrigerant we can save and environmental impact, carbon footprint reduction, all that kind of stuff. That's for a good study. So if you just search that, it'll give you some stuff maybe you can also talk about.
Thank you, Jim.
Yep.
You're always so helpful.
Oh, no problem.
All right, guys, check out the next measureQuick video when it comes out, and we'll all see you then.
All right. Thanks, Jen.
Thanks, Jim.
Bye.
Bye.